Okay, so this is the part two of performing rainfall runoff modeling on a catchment stream system using GIFMod. In this part of the video, what I'm going to do is that I want to add infiltration. In reality, uh, very rarely we have cases where all the precipitation becomes runoff. Usually, part of the precipitation turn into basically infiltrates to the ground. Some of it may also evaporate. I'm not going to go through evaporation, even though you can easily add evapotranspiration to any block, including the surface water and soil. But I'm not going to go through that in this video. So so basically, if you remember, this was our conceptual model. So what we did was we created this catchment, which basically in part one was impervious, and then we had the stream, and then we had a boundary condition. And now all I'm going to do is that I will add a soil layer, and I'll add a groundwater layer, and then I'll connect them to each other, and I'll let infiltration happen. As I did in part one, what I'm going to do is that I will run the model, it kind of sort of as soon as I kind of add the several components to make sure that it's working and to make sense of the results. So what I'm going to do is that I want to discretize the soil layer into essentially three layers. Now these layers, in this case, what I'm going to assume is that they are homogeneous, but you can always let them have different properties and so on. So as you can see, the elevation of the centroid of the surface is 125 meters, and the elevation of the groundwater is 122 meters. So basically the depth of the vadose zone is 3 meters, which I'm going to discretize into three layers, each of them having a depth of 1 meter. And then what I'm going to do is that I'm going to do it in two stages. Basically, the first one, I will just fix the groundwater table. I will not allow it to change. So I treat the groundwater as sort of a boundary condition. And then, but if I do that, then I can't really, model base flow. For example, if there's a flow from groundwater back to the stream, or vice versa. So the next step, what I'm going to do is that I will release that constraint on the head of the groundwater, and then I'll allow flow from the groundwater to the stream. Of course, all of these things are going to be based on certain assumptions that I have to make, but I'll explain those as we walk through this demonstration. So let's do this. Basically, what I'm going to do is that I will add the three soil layers. So let me first create the first soil layer. So this is the first soil layer that we have. I want to initially use a soil layer that its permeability is low. So what I'm going to do is that as a subtype, we can actually select the type of soil, and all the soil retention parameters and saturated hydraulic conductivity and other properties will be determined based on the soil type. So what I'm going to do is that I'll assume that the soil is clay, okay, and I assume that all three layers are basically clay, and then later on I'll change it to another soil type that is more have a higher hydraulic conductivity, and we can see what the effect will be. So I'm going to pick clay. Then the bottom area of this soil block is going to be the same as our catchment. So if you remember, the catchment had a bottom area of or a surface area of 10,000 square meters. So this is going to be 10,000 too. The bottom elevation, if I want the soil layer to have a basically each soil layer to have a depth of 1 meter, then I know that the elevation of the center of the catchment is 125. So the elevation of the soil layer will be, this soil layer will be 124. And then I'm gonna so a few things. First of all, based on the soil type that I picked, I got some basically soil parameters populated. You can always go and change these if you have some data on what's, for example, the hydraulic conductivity of the soil, or what's the specific, for example, Van Genechten alpha parameters and so on. But I'm going to leave them at this time. But the moisture content, what I'm going to do is I'll pick a larger value. So let's see what's the saturated moisture content. So this is a saturated moisture content or theta sub s, which is 0.37. I'm going to go with kind of a high moisture content of 0.35. And the reason I do that is I want the model to reach a steady state or quasi steady state or equilibrium condition faster. Okay, so I'm going to go with a moisture content of 0.35. The other parameter that I need to specify is the depth of the soil layer. So here's the depth, and I'm going to go with the 1, right? And that's pretty much all I need for this layer. Now, what I can do is that I can create an array of this soil layer, but I'm going to avoid that right now for this example. I'm going to just create the other soil layers manually, okay? So I'm going to do this. This is the second soil layer. And I want to make sure that I'm going to specify all the needed parameters. So the subtype is going to be, again, clay. The bottom area, again, is going to be 10,000. The bottom elevation in this case is going to be 1 meter lower than the topsoil layer. So it's going to be 123. Then the moisture content, again, let's make it 0.35. The depth is going to be 1, and then I think I'm all set, right? And then let's go and do the third one. Okay, so I'm going to add another soil layer. This is going to be my soil 3, and I'm going to place it here. And same thing. So let's do the subtype being clay, the bottom area being 10,000. The bottom elevation this time is going to be 122. Then the moisture content, I mean, if I want to get close to a steady state condition, I expect this lower soil layer that is close to the groundwater to have a higher moisture content. So let's just make it 0.38, which means it's saturated, right? So the bottom one is saturated, and the depth is again 1 meter, and that's pretty much it, right? Now let me save this as, I'm going to save it as with a new name. Okay, so I'm going to call this Rain-Runoff with infiltration. Then the next step, let's just connect. So what I'm going to do is that I'm going to connect my catchment to soil, and I'm going to connect this soil layer to another one. I'm going to connect this soil to another one. And then all I have to do is to basically indicate the length of these connectors. So the length of this is a vertical connector, if you imagine. So it's basically vertical, basically something that connects from the center of the surface to the center of the top layer. So the first connector is going to have a length of 0.5, okay, half of the depth of the soil. And that's what I'm going to do. I'm going to say this is 0.5 meter. And then the other two are going to have a length of 1 meters each. So this is going to be 1 meter, and this is going to be 1 meter. And by the way, a few things. I don't specify for the several of the parameters that I could. One of them is saturated hydraulic conductivity. So if I don't specify saturated hydraulic conductivity, what happens is that the model will interpolate the saturated hydraulic conductivity from the two soils that were connected. So since I have saturated hydraulic conductivity for the two soil layers that I connect to each other, I don't have to specify the value here. Same thing with the interface cross-section area. So this is going to be taken as essentially the average of the bottom area of the two soil layers that are being connected. Now if I wanted to connect two soil layers horizontally, then I needed to specify this interface or cross-section area, and that would have overwrite the calculated value based on two soil layers that are being connected to each other. So that's pretty much it. Let me save this. So at this time, actually, I can run the model. So I started from the model that we created in part 1. So all the model, basically my precipitation data and the duration, simulation, everything is set. So now we can actually run it. Now, keep in mind before running the model is that the water that infiltrates to the soil, it cannot really drain. So after I expect that by soil to get saturated after some time the simulation, and then no more infiltration is going to happen because the soil is going to be completely saturated and the water will not have any way to drain from the soil. So in the next step, what we're going to do is that we're gonna basically add some sort of a boundary condition that will allow basically the water to be drained from the soil, right? So okay, let's go on. So I'm going to just sometimes I need to click 2 times on the run button in order for the simulation to start. So okay, so this is it. So we did the simulation over 1 year period. Now let's look at some of the results. So so basically, first thing, let's look at the infiltration flow. So if you look at the infiltration flow, this is what we're going to get. Initially we have some infiltration, and then after some time it goes to 0. And the reason for that is the soil will be saturated, right? So now I can check that. I can look at soil 1, for example, and I can look at the moisture content. And as you can see, the moisture content will go up. Now the saturated moisture content was 0.38, but the fact is that there's some essentially storativity in the soil. So GIFMod allows the moisture content to go above the saturated moisture content, but that means that we're going to have a positive head. So now if I look at, for example, the head here, the hydraulic head of my top layer, as you can see, it's not 120, it's 124.8, which is above this layer, or actually maybe more. Maybe it's more about 120. It gets to 125, anyways, which is what should happen. Now I can look at, let's say, the bottom soil layer again. You can look at the moisture content, and you'll see that the moisture content will go even higher, and the head, I assume, is going to be higher than 125 because of the hydrostatic pressure. So you can look at the head, and as you can see, it's again, it's 125, but anyways. So okay, let's do this one. So we can look at the flow. So as you can see, we have this negative flow at the beginning. The reason for that is that we started from a high moisture content in soil 3, so there was some matrix potential in soil 2 initially, and that led to an upward flow until the system got into a balance, and then we have positive infiltration or percolation after that. Okay, so that's that. So now let's go to the next step. So the next step, what I'm going to do is that I will add basically a groundwater layer, right? I can basically, as long as I want to fix the head, I can use any block and then fix the head. But I'm going to use this thing called Darcy block, which is supposed to represent saturated aquifers. So I'm going to add the Darcy block here. I'm going to set some parameters which may not necessarily matter. So if you don't, it may not really affect. But to make sure, to just enter everything correctly, I'm gonna still enter them. So what I'm gonna do is, first of all, the bottom area of this is 10,000 square meters. The bottom elevation, let's say our groundwater, I haven't specified anything on my on the diagram, but let's say this groundwater, the thickness of the aquifer is 2 meters, right? So basically what I'm gonna do is that the bottom elevation here therefore will be 120, okay? And then we can, so the depth is going to be 2 meters. The saturated hydraulic conductivity, I mean, this is default value. We can change it, but I'm going to keep it at the default value. And then the other thing is, okay, so basically, in order to make sure the system will not be saturated, what I can do is I can set I can fix the head of the groundwater. So basically I can say the groundwater table is at 122 and it's going to stay at 122 no matter how much water enters the groundwater block, right? So that's a way of treating that as a kind of a fixed boundary condition. So what I'm going to do is I will fix the head storage relationship at 122. Now there are certain parameters that we have to enter, otherwise, GIFMod will give us errors, even though they're not going to affect our simulation because we fixed the head storage relationship. But then we need to specify the initial moisture content. So let's say the initial moisture content is 0.4, and then also the saturated moisture content of the Darcy block. So I'm going to make that also 0.4. Okay, so that takes care of our Darcy block. Then what I'm going to do is that I will just add the soil layer to the Darcy block, and then all I have to do here is I assume to indicate the length of this connector. Now the length of this connector, what we consider to be the length of the connector depends a little bit on our judgment. Now since this was the groundwater table was 2 meters deep, and then the soil was 1, I'm gonna basically just consider the length to be the distance from the centroids vertically, which will be 1.5 meters. Okay, so this is going to be 1.5 meters, and then I'm going to save it, and then now let's just by the way, yeah, let's just run it. Okay, so I'm going to run the model. Okay, the simulation is finished. Now let's look at certain things. Let's look at, for example, I can now look at the runoff and then compare it to, I don't have the runoff before I added infiltration, but if I can now go and look and basically check and compare them. So as you can see, there are a lot fewer events that will result in surface runoff because we have infiltration. Still, they are significant, and the reason for that is that we picked clay to be our soil type, and clay has a low hydraulic conductivity. If you pick sand or something with higher hydraulic conductivity, I'm sure there will be less of these. Maybe only in some extreme events you will see some runoff. And then we can look at the infiltration. So I can look at the infiltration. So this is it. So infiltration is happening all the time. And this is a rate of infiltration. And I can, so if I want to look, for example, at the recharge into my groundwater, I can look at that. So this is the recharge in the groundwater. Again, what you see a negative flow at the beginning. And the reason for that is we have some positive pressure in the groundwater. So the head at the beginning, the head of the groundwater is, or maybe we have some drier soil up there, and then you have some upflow at the beginning, and then you have, but the system becomes stabilized pretty quickly, and then this is our recharge rate. If I want to look at my the total amount of flow that infiltrated to the ground, I can look at the storage of the Darcy layer. Okay, and as you can see, of course, initially we had some storage. We had 8,000 cubic meters, but it got to 15,000. So that's how much infiltration took place over the course of the simulation. Okay. Okay, so that's what it is. Now next thing, let's say what I want to do is I want to let some of the groundwater to basically go back to the stream as base flow. Now that requires some level of assumptions. If you have some, you may have a case when you have some information about that you can use to basically, for example, I don't know, calibrate maybe your model or adjust the parameters so that you basically do this correctly. But I don't have that, so I'm going to make some assumptions. So let's say this groundwater basically goes below the stream, right? And then what I'm going to do is that I will now connect my. I need to do certain things. I mean, first thing I'm going to do is if I want dynamically to model the base flow from groundwater to the stream, I can't really use the fixed head storage relationship. So basically I have to go and delete this so that now the head of the groundwater is going to be dynamically calculated, right? Then the next thing is that I'm gonna connect my groundwater layer, or Darcy layer, to the stream. Okay, so we have this connector, and then to make sure that this works, I'm gonna basically indicate what type of connector this is, because I'm not sure if GIFMod will assign the right type of governing equations to this connector that connects the Darcy layer to stream. Probably will, but just to make sure. So I'm going to change the type of my connector from default to Darcy. Okay. So what I'm saying here is that the Darcy equation is governing the flow from groundwater to the stream, or vice versa, right? And then I need to specify an interface cross-sectional area. So what that is the area, the interface area between groundwater and the stream, right? So let's say, we made the assumption that the stream had basically it's 100 meters long and it's 1 meter wide, right? So the area, so if the groundwater comes from all the bottom of the stream, then it makes sense for the cross-sectional area to be 100. So I'm going to say 100 meters. And then I can also specify the saturated hydraulic conductivity, even though if I don't, it's basically going to be the saturated hydraulic conductivity is going to be taken from the Darcy, but I'm going to specify. So I'm going to use maybe a larger number. So I'm going to say 3 meters per day, and then the length is that's tricky. We don't really know how to say what the length is. If I want to go with it really depends on my judgment and so forth. If I want to go with centroid to centroid, it's going to be something like 50 meters. I don't know. I'm just, that's maybe this can be treated as a calibration parameter. I'm going to just go with 25 meters, just for the sake of, making some assumption. Okay, so I'm going to save this model, and so now I think everything should be ready. Let's just start basically the simulation. Okay, so simulation is done. Now we can look at some results. So this is the first thing that we might be interested in. We want to see how much base flow actually occurred. So I'm going to right click on this connector connecting a Darcy block to the stream block, and I'm going to say plot flow, and this is what you see. So basically you have some base flow that is basically fluctuating, and its value is pretty small compared to the surface runoff in this case. I assume if I change the soil type to sand, this is going to be increased. I can look at my infiltration to the groundwater layer. So this is what we're gonna get, and then I can also look at my maybe the flow going out of the system. Now that we have base flow, the flow does not go to zero, completely zero. So basically, you can look. So as you can see, we have some base flow, and that was it. Thank you for watching, and look for my future videos.